Have you ever imagined a ground-based vehicle that could move faster than an airplane? It sounds unbelievable, but this is the new technology quietly challenging the entire aviation industry. T-Flight, a super high-speed system that combines magnetic levitation with a low-pressure environment, engineered to reach speeds above 1,000 kilometers per hour, fast enough that even the horizon can't keep up. And the vacuum maglev is considered the most ambitious project in modern transportation that China is currently developing. An effort to turn concepts and experimental models into a true ultra-high-speed network where journeys spanning thousands of kilometers can be compressed into the length of a short film. The T-Flight project is not just a new means of travel, it is a declaration that humanity can bend the limits of speed if the engineering is bold enough. In this video, Mandarin Tech invites you to explore how T-Flight is designed and why it could become the foundation for an entirely new era of transportation. 1. Over the past 3 decades, China's economy has shifted rapidly toward urbanization, driving the demand for connectivity between major cities to grow far faster than what existing transportation systems can support. High-speed rail has opened a new era of mobility, but as both speed and urban density continue to rise, tens of millions of daily trips are beginning to create unprecedented pressure on traditional transport networks. At the same time, international projects have begun introducing new approaches. Japan is advancing the Shinkansen at a speed of 320 kilometers per hour, and Shanghai is developing its maglev line reaching 460 kilometers per hour. Yet both still struggle to meet the speed requirements of emerging megaregions, where tens of millions of people travel each day. These research directions revolve around 2 core pillars: eliminating contact friction and reducing air resistance to the lowest possible level. This is also why China is developing T-Flight. By combining magnetic levitation with an environment in which air resistance is nearly eliminated, the system is designed to achieve speeds far beyond any ground-based vehicle ever created. Although still in the research phase, T-Flight represents an effort to build a new layer of transportation as fast as aviation but as stable and controllable as rail. In the future, once completed, this technology could shorten inner-city journeys from hours to just a few minutes, transforming distances once considered far into seamless connections within a new generation of urban networks. Magnetic levitation technology is not a concept that emerged only in recent decades. Its earliest foundations were established more than 100 years ago, when European scientists began experimenting with using magnetic fields to lift and propel an object without physical contact. However, the technology of that era was not advanced enough to turn the idea into a real product. By the 1960s-1970s, Germany and Japan became the 2 pioneering nations in developing the first modern maglev trains. Germany pursued the Trans-Rapid system, focusing on high-speed performance, while Japan developed the SC maglev, which uses superconductivity to generate stronger and more stable lift. These prototypes laid the groundwork for later commercial maglev systems. The first major breakthrough came in 2002, when Shanghai launched the Shanghai maglev line, using Germany's Trans-Rapid technology and reaching a commercial operating speed of 430 kilometers per hour, making it one of the fastest trains in the world. However, despite being impressive, traditional maglev systems are still limited by air resistance. And it is precisely this barrier that led to the emergence of more ambitious research, such as T-Flight, where magnetic levitation is combined with a reduced pressure environment to create the next generation of ultra-high-speed transportation. At the core of T-Flight is magnetic levitation technology, a principle that allows the passenger capsule to avoid any physical contact with the guideway, unlike traditional vehicles. When the magnetic system is activated, the magnetic force instantly lifts the entire train body by several millimeters, creating a stable, floating state. With no wheels and no sliding friction, nearly all vibrations disappear, resulting in a movement far smoother than current high-speed trains. Eliminating mechanical friction enables T-Flight to tackle an even greater challenge, reducing air resistance. By placing the train inside a low-pressure tube, most of the air in front is removed, causing drag to nearly vanish. In this near-vacuum environment, the train can accelerate rapidly and maintain extremely high speeds without consuming excessive energy. Thanks to the combination of magnetic levitation and a reduced pressure tube, T-Flight is designed to reach speeds above 1,000 kilometers per hour, approaching the cruising speed of many commercial aircraft, such as the Boeing 737. What captures the attention of engineers is not only this headline speed, but the ability to maintain a stable floating state at such velocity. No jolting, no noise, and movement as smooth as gliding through air. Superconducting magnets provide lift and guidance, precisely controlling the train's trajectory. When paired with a fully sealed tube, T-Flight achieves near-optimal operating efficiency, low energy consumption, minimal air disturbance, and high stability. If commercialized as designed, the journey from Beijing to Shanghai could be reduced to under 2 hours. Faster, smoother, and far more energy efficient, marking a significant leap forward in high-speed transportation technology. Currently, T-Flight is still in the testing phase in China, using small-scale reduced pressure tubes and prototype capsules operating at medium speeds to evaluate stability. Engineers continuously measure vibrations, the temperature of the superconducting magnets, and the system's ability to maintain low pressure inside the tube. Some tests have exceeded 600 kilometers per hour under simulated conditions, demonstrating the potential to approach 1,000 kilometers per hour once the full system is scaled up. However, all results so far remain preliminary steps before moving toward large-scale outdoor testing. T-Flight, China's ultra-high-speed vacuum tube rail project, is expected to create a 1-hour economic circle, where travel between major cities becomes extremely fast. When geographic distance is no longer a barrier, trade, investment, logistics, and workforce movement can all grow more rapidly. By replacing short-haul flights that consume large amounts of fuel, T-Flight has the potential to reduce carbon emissions and contribute to environmental protection. Overall, T-Flight is not just a new mode of transportation, but a bridge connecting speed, economic growth, and ecology. A step forward that cities, economies, and the planet could all benefit from if the project is successfully realized. Despite its enormous promise, T-Flight still faces significant challenges. The first is cost. Building a low-pressure tube stretching hundreds of kilometers would require an investment many times larger than that of a traditional high-speed rail line. Next is safety. Operating a passenger capsule in a near-vacuum environment demands perfect airtightness and the ability to control risks at speeds over 1,000 kilometers per hour, where even a minor deviation in magnetic fields or pressure could lead to unpredictable consequences. T-Flight must also compete in a landscape where many countries are pursuing their own approaches. Japan is developing the maglev using superconducting technology. The United States and Europe are testing hyperloop variants, while South Korea, China, and Germany continue to upgrade next-generation maglev systems. This race is not only a technical challenge, but also a competition for funding, national strategy, and the right to shape global transportation standards in the future. If T-Flight represents the future, then the Shinkansen is the symbol of the recent past, a system that has proven the power of optimization rather than technological revolution. With a commercial speed of 320 kilometers per hour, the Shinkansen sets the highest standard for reliability thanks to its automated control system, artificial intelligence, and real-time monitoring. The modern E5 series can track thousands of sensors on its wheels, brakes, and engines, processing data instantly to detect anomalies and trigger automatic maintenance when needed. As a result, in more than 6 decades of operation, Japan has never recorded an accident involving the Shinkansen. The Shinkansen's signature long nose is actually inspired by the beak of the kingfisher, a bird capable of diving into water with almost no splash. Japanese engineers realize that this streamlined shape helps reduce sudden pressure changes when the train enters tunnels. If the nose were too short, compressed air would create a loud tunnel boom along with vibration. By adopting a kingfisher-inspired design, the Shinkansen runs fast while maintaining its characteristic smoothness and quietness. Instead of pursuing a low-pressure tube environment like T-Flight, the Shinkansen relies on an improved traditional rail system. a choice that allows Japan to build infrastructure at a far more reasonable cost. Shinkansen trains can operate directly on the existing high-speed rail network, making use of stations, signaling systems, and established corridors that have been refined over decades. This difference is also evident in the train's interior capacity. While modern maglev systems, such as the maglev, are limited in space, with only about 68 passengers per carriage, the Shinkansen can carry up to 100 passengers per carriage. This gives the Shinkansen higher transport efficiency in real-world conditions, especially on routes with heavy passenger demand. In its effort to elevate the Shinkansen to a new speed standard, Japan introduced the Shinkansen Alfa X, an experimental train considered the most ambitious since the first generation in 1964. Alfa X is designed to reach operating speeds of up to 360 kilometers per hour, and it can even approach 400 kilometers per hour in test runs. Its most striking feature is the 22-meter nose, an advanced aerodynamic structure that reduces noise and eliminates shock waves when the train enters tunnels. Inside, an active vibration control system and a new electromagnetic braking unit allow the train to maintain high speeds while ensuring exceptional stability, a hallmark of the Shinkansen. With Shinkansen Alfa X, Japan is not trying to surpass physical limits like T-flight, but instead pursuing the philosophy of pushing traditional rail technology to its absolute maximum. If T-flight represents the effort to push beyond physical limits to aim for speeds above 1,000 kilometers per hour, then the Shinkansen demonstrates that speed, reliability, and high passenger capacity can be achieved through the optimization of existing technology. This approach has enabled Japan to build a system considered the global model for high-speed rail. And it is precisely this contrast that paints the full picture of today's speed race. T-flight pursues a revolutionary leap forward, placing its bets on a technology that has never operated at full scale. Meanwhile, the Shinkansen continues to prove the strength of an improvement-driven philosophy, where every millimeter of design and every control algorithm is refined to near perfection. Two different approaches, yet both aim at the same goal: redefining how humans move. This rivalry is not merely a contest between two technologies, but a reminder that the future of transportation may not belong to a single solution, but rather to the convergence of bold breakthroughs and time-tested experience. Looking back at the entire journey, it's clear that the development of high-speed transportation has never followed a single path. Each country and each project reflects its own philosophy. Some choose a cautious approach built on proven technologies, while others pursue bold ideas with the ambition of redefining how humans move. T-flight and the Shinkansen are just two representative snapshots in that broader landscape, where innovation and tradition constantly coexist, complementing and challenging each other to push transportation forward. In the global landscape of transportation, what sets each approach apart is not only the technology chosen, but the way each country defines its objectives, prioritizing absolute speed or pursuing sustainable stability that aligns with real-world needs in its own urban structure. Thank you for following this journey with Mandarin Tech. Stay with us as we continue exploring the technological projects that may shape the world of the future.